Hi guys, it's Mr. Thompson, and today I want to talk with you a little bit about ideal gases, what an ideal gas is, and then also how to do calculations. We're going to get another formula today, so let's jump in. We talked about before 1 mole of gas at STP will occupy 22.4 liters, but I didn't talk a whole lot about what if the pressure is different, or what if the temperature is not 0 degrees Celsius, or the amount of gas, maybe we have more than a mole, anything like that. So we're going to kind of branch out a little bit further, and we're going to use a formula, and this formula is going to allow us to calculate values for ideal gases. Now, ideal gases, they'll have some certain properties, and if we take a look at these properties, the first one, a single molecule of an ideal gas has no mass or volume. So they're assuming that individually the gases aren't really anything, like we don't have to worry about it on a piece-by-piece basis. And I know that's not very realistic, but just bear with me for just a minute. The other property of an ideal gas is that the molecules have elastic collisions, and that means they bounce off of each other perfectly. They don't slow down, nothing happens. They just, if the molecules happen to collide, they bounce off perfectly and they keep going. So both of these real expectations aren't actually very realistic, but it turns out that real gases will act like ideal gases a lot of times. So it's not too unreasonable for us to do this. Please make sure you understand. There's no such thing as an actual ideal gas, but real gases, which is what we deal with every day, real gases can act like the ideal gases in a lot of senses. Okay, I know that seems a little bit confusing, but mainly what we're wanting to get out of this is the formula. The ideal gas law. It will relate pressure, volume, the amount of gas, and the temperature. And the formula looks like this. PV equals nRT. Okay? Now R is something new. R is the ideal gas law constant. It is a constant. Its value is always the same. But the problem is that it will change. I know this is going to sound weird. The value of R will be different depending on what the problem gives you. Now these values are always constant, but they're different. Now I want you to really look. Aside from the numbers, there's something about each one of these that is different each time. If you notice, this one's in atmospheres, this one's kilopascals, and this one is millimeters of mercury. So in each one of these, the pressure has a different unit. Notice they're all liters, moles, Kelvin, liters, mole, Kelvin, liters, mole, Kelvin. But the pressure has a different unit. So what do? You, first of all, do not have to memorize any of these values. I will always give them to you. Your formula chart will have them. You will not have to memorize them. But you will have to pick the correct value. If you pick the wrong one and use it, you will get the wrong answer. Now, picking the correct value is easy. All you have to do is pay attention to your pressure in the problem and pick the one that matches it. If your problem gives you millimeters of mercury, then you're going to use one value, but if it gives you atmospheres, you'll use a different one. Now, before we jump into practicing with these problems, there are 3 steps that I want you to follow when you use this. Every time I want to see these. First, write down the variables given in the problem. And when you do that, choose the correct R value. Second, solve for the variable you need using algebra. Don't go plugging in numbers until you have the variable by itself, just like we were doing before. And finally, plug in numbers that you wrote down in step 1. So let's take a look at some of these examples. Let's jump right into them. Okay, here I have a sample of oxygen gas. It gives me the pressure, it gives me the temperature, and it gives me the volume. It says how many moles of oxygen are in here. Okay, so first things first, I'm going to write down all the variables that it gave me. It gave me the pressure, it gave me the volume, it did not give me the number of moles. So that's what I'm looking for. I'm looking for N. Now, it gave me temperature, but if you notice, it gave me 25 degrees Celsius, and I have to convert that to Kelvin. We always convert our temperature to Kelvin. So I wrote 298 Kelvin. I just added 273 to 25. Now finally, we need to pick the correct R value. So we go back in our notes and look, the pressure was given to me in atmospheres. No problem. I'm going to look for the R value that has atmospheres, and this is the one that I'm going to use. Now step 2, we're going to write our formula, and I'm going to get everything away from the variable I'm looking for. So I'm looking for N. I need to get rid of R and T. I'm just going to divide both sides by R and T, and that's what I get. Simple and straightforward. And now I can plug in my numbers that I wrote down, the 1.3, the 2.5, the R value, and the temperature, and I get 0.136 moles. As long as you're doing all these steps, they really make these problems simple. Write down the variables, solve for what you need, and then plug in numbers. It cuts down on so much confusion if you get in this habit. Let's check out another one. This time, I have a 250 liter sample that contains 20.3 moles, and the pressure is 143 kilopascals. It says at what temperature in Celsius, that's going to become important in just a moment, what temperature is this sample being held? Okay, let's write down everything. Here's my pressure, here's my volume, here's the number of moles. I don't know my temperature, but using all of this, I'm going to pick the correct R value. Kilopascals, pick the one that has kilopascals in it right there. And this is the R value I'm going to use. Same thing as before, PV equals nRT. This time I want temperature, so I'm going to get rid of these two guys. I'm going to divide both sides by N and R, and it gives me this. I'm just going to plug in the numbers. Oops, I should have written T there. That's a mistake for Mr. Thompson. But I plug in these numbers, and I get a temperature of 211.92 Kelvin. But the problem wanted it in Celsius, so I'm going to subtract 273 from that to go back to negative 61.1 degrees Celsius. Very, very cold. This is a very cold sample of neon gas. All right, one last example problem. At what temperature is a 5-gram sample of neon gas if the pressure is pressure on a 19-liter container is 256 millimeters of mercury? Okay, we've got two problems here. First of all, you see the millimeters of mercury. We're going to have to make sure we take care of that. But the other problem in this question that we have to take care of is we normally measure the gas in moles, and this says grams. So our very first step in this problem is we are going to convert the grams of neon gas into moles. So I'm going to do that. I'm going to put it over 1. Molar mass of neon is 20.180. Multiply that out. I have 0.248 moles of neon. So I can write that down. Of course, here's my pressure and my volume. I don't know the temperature, but I'm going to pick the correct R value, the one with millimeters of mercury, and that was the 62.4. PV equals nRT. Solve for T. Plug in my numbers. Oh, I left that N in there again. And get an answer, 314 Kelvin. And you say, well, do I have to convert that to Celsius? Since the problem didn't ask for it, no. I'm not going, if I don't ask you for it, I don't expect you to do it. If I want you to convert to Celsius, I will do that. I will say, please convert this to Celsius. All right, that's it for this video, guys. As always, if you have any questions, you can feel free to email me, or you can just talk to me in class. I'll see you guys tomorrow.